An important aspect of reactive programming is scalability, specifically that we favor scalability over performance. The distinction I am making here is that performance focuses on when the system is used by a single client. Making the system faster in this case will usually involve optimizing it for running on one CPU, for example, which is as fast as possible. But when multiple clients use the system, these optimizations mean that there is a ceiling which will be reached, and beyond a certain point, the system will not scale anymore. It will not be able to process the inputs received from these multiple clients anymore. Sketching this graphically, I have here the number of clients, and here the requests per second. And optimally, this would be what clients want, because every new client adds just to the requests per second that the system can handle, which means that the response time will stay roughly constant. In this case, let us say it looks like this. Of course, a real system will have a maximum, say here. And that means that the real performance curve will look somewhat like this. And what that translates to in terms of response time is something like that. So when I say focus on scalability instead of performance, that means moving this red line as far up as is practical. And this will make your system withstand a higher number of clients without compromising the service quality, as would happen in this case here. You want to move the point where the response time explodes as far to the right as possible. What does that mean in terms of implementing an actor system? We learned that one actor can process only exactly one message at any given time. It cannot do more work just because there are more messages coming in. You need to have multiple actors working on the incoming requests in parallel in order to make the system with more requests per second. One pattern we have already seen in the link checker example is to start new actors for every request. Another one is that you can have replicas of actors which perform a certain task, and if these actors are stateless, then these replicas can run concurrently. Let's say you have an actor here, for example, calculating mortgages. And when a client requests, it sends a message, and then the mortgage service will calculate the conditions and reply back with an interest rate, for example. Now, if this calculation is moderately complex, then it will take some time, and we could, for example, scale it out by having multiple workers to perform the task. It is not necessary to have one per request. It could be a pool of, say, 5 or 10, and then they can use at most 5 or 10 CPUs completely for this purpose. By not having one actor per request, it is easy to limit the parallelism which is allowed. Since actor communication is conveniently asynchronous message passing, the client here does not know whether the mortgage service does the calculation itself or whether it has farmed it out to any of the workers. This means that asynchronous message passing gives us the possibility for vertical scalability, which means using more CPUs in the same node. The purpose of this mortgage service in the last example was just to route the incoming requests to the pool of workers. And there are different schemes for doing that, which we shall look at in the following. These schemes can be grouped into stateful or stateless routing. Stateful means that the routing algorithm itself needs to keep some state. For example, round robin needs to keep a counter. We will see what that means in detail. And in general, stateless routing might be preferable, because that can even happen in parallel by multiple routers, because they don't need to share anything. The most easily understood routing scheme is the round-robin one. You have the router here, incoming messages, and let's say we have 3 targets, 1, 2, and 3. Then the first request will go here, the second will go here, the third will go here, and then it starts over. Always 1, 2, 3, 1, 2, 3, 1, 2, 3. This means that the distribution of messages to these routees here will be quite close to equal at any given point in time. But that also means that if, for example, actor 1 here experiences a failure and the restart takes a bit, then it will still receive the same incoming rate of messages. So the mailbox of this one will get more full than the other two. And that means that messages which go to number 1, which is 1/3 of the incoming messages here, will experience a higher processing latency, because there is a mailbox in here which the actor needs to work off in order to get to the current message. This can be fixed, of course, by looking at the mailbox size and routing only to those which have the lowest number of messages currently. This requires all the routees to be local so that the message queue can be inspected. It obviously does not work over the network. And also, the cost of looking into the mailbox and counting the messages in there is rather high. These data structures are concurrent and need to be properly synchronized, and they are not as cheap to traverse as a normal collection is. This means that this routing cost is rather high and only worth it if the job to be performed takes more time than that. But in that case, the imbalances introduced between different processing speeds of the actors are evened out by the algorithm, and the latency which is experienced by clients is more consistent. Taking this model to the extreme means sharing a work queue between different actors. So what we have here is just a queue for the messages, and then we have our routees here, and they always process the oldest message in the queue, and effectively everyone pulls from there. Messages go in on top. The most efficient implementation of this scheme is that they really do share the same work queue. There is in akka the balancing dispatcher for achieving that, but that requires the routees to be local again. Of course, this will give the most homogeneous latency which you can achieve. So far, evening out imbalances came with a rather high cost of routing itself and or the need for the routees to be local. If we sample the imbalances, for example, over time, it can be rather coarse. It doesn't need to happen per message. It could be once per second, for example, or even less frequently. Then we can gather these data and use them to steer the routing weights. So if we have here the incoming message stream, and here this adaptive router and the routees will periodically send back the feedback of, for example, how full their queue was at this second, or what the CPU load is on that node, because they could run on different nodes. And then this one has an algorithm inside which uses this information to change the relative weights of where messages shall go. For example, more frequently here, less frequently here, if this node is currently under more load. This can be a good compromise, but it requires the steering of these weights to be done carefully, because otherwise you can introduce oscillations or over dampening so that the reaction times are longer than necessary. And for that, you need to look into feedback control theory. The routing algorithms we looked at so far have all been stateful. The router itself needed to keep information. For example, the round robin needed a counter where the last message was sent. This can lead to some routing overhead because the decision depends on something which is shared. If you use random routing, for example, then in principle no router is necessary. We have the incoming message stream, and we have our routees. And each sender of a message to this set of actors randomizes on its own where the actual message goes. That means that there doesn't need to be an intermediate actor here which does anything. This offers the lowest possible routing overhead. The problem with it is that the process is random, so there is the probability that, for example, number 1 might, for a certain time window, get more messages than 2 and 3. Asymptotically, these will even out, but in the real running program, it might be observable. Another stateless routing scheme is that of splitting up the incoming message stream consistently according to some criterion. So we have our routees again, and then let's say we have the black part, the red part, and the green part of the message stream. And all messages which match this green color always go to routee number 3. This means that there also does not need to be a central authority here doing the routing, but it also means that these substreams need to be chosen such that they are of equal weight. Otherwise, it will lead to systematic imbalances between the processing times for the 3 routees. This scheme has another advantage. Up to now, it was not really deterministic which message comes to which node or which routee. So 1, 2, and 3 needed to be identical actors, and if another request comes in later, it will have no correlation, or it cannot have any, cannot require any correlation with an earlier request, because the state of these 3 actors is not shared. Splitting up the message stream according to some criterion allows us to, for example, have all requests pertaining to a certain user go to this actor. And if the user is the important state to be kept, then, well, everything pertaining to my user, for example, always goes to routee number 1. And then subsequent messages could have a common interest correlation because they all go to the same target always. And updates to my user, for example, at number 1 would be safe because later messages will see the updated state. This means that consistent hashing routing can be used to replicate stateful actors. This requires that the input stream of messages can be split in such a fashion that the state affected by these substreams is independent. If a certain part of the state is shared between several actors, we have seen that in a previous lecture with this distributed store. You have 2 actors here, A and B, and if they share something which shall be the same, then they need to communicate. We have seen that, and they need to exchange data in appropriate data structures so that they can achieve eventual consistency. Here, replication is not used for scalability so much, but it can also be used for fault tolerance. And while we are at that topic, it is quite easy to see that persistent actors, persistent stateful actors, can be replicated as well. When something goes wrong, we just need to recover the actor, and that could well happen at a different location. For example, if the node where the actor was living, let's say node A, we have our actor here. If that node crashes and is not recoverable, then on node B, we can just replay the state of actor A and resurrect it. This will also require a certain message router, which first sends messages here, and then after the crash, switches to the new instance. And if we are using event sourcing, we can even optimize this process. This second copy of A could be started right away, but it could be inactive and only replay the event stream which is generated by A, so the event store. And then recovery of A in the event of failure takes very little time. All the features seen so far have been made possible by the design of the actor model. Asynchronous message passing gives us vertical scalability, so the ability to run a process in parallel on the same node on multiple CPUs. And location transparency, which means hiding everything behind ActorRef and remoting does not look different, enables horizontal scalability. That means running the computation not on one node, but on a cluster of potentially hundreds of nodes.